Hi, everyone. Welcome to the FORCE seminar. Thank you for joining us today. I'm Kara Brugman. I'm a research scientist and the outreach coordinator at FORCE. Oh, you're muted, Kisei.
Yeah, I'm Kyusei Tsuno. I'm also the research scientist of the FORCE program. And we are interested Dr. Bin Chen, Bin in the researcher at the Hawaii Institute of Geophysics and Planetary, University of Hawaii at Manoa. So he will talk about the title Pushing the Limits, Investigating Volatiles in Planetary Interiors under Extreme Conditions. And thank you, Bin, for contributing the talk for us. So it's all yours.
Real quick before we start talk, I just want to remind everybody
that
you can see a video of our previous seminar with Sally Jean Tracy. It's up on YouTube right now at bit.ly/FORCE. The video of this seminar will be posted next week. And you can sign up for the listserv on our website, force.asu.edu, to get updates on all of our events. We have one more seminar this semester with Yingwei Fei from Carnegie Earth and Planets Laboratory, formerly Geophysical Laboratory. That will be on Friday, May 19th at the same time at noon Arizona time. After that, we'll reconvene in the autumn. All right, so I will stop my share. And then you can go ahead.
Okay. Can you see my screen?
Yes,
okay.
We can see your screen. Yeah.
Thank you very much for the kind of introduction and also for organizing this seminar. So today I'm going to talk about our recent work on volatiles, basically, so deep volatiles in planetary interior under extreme conditions. So before I start my main part, so I will show you a short video that I made with my student. So we use diamond anvil cell for our research. And so this is a type of diamond anvil cell. It's called a BX90 diamond anvil cell. We put a heater inside the diamond anvil cell so we can heat up the sample at the same time. And then this is another high pressure device that we use. This is the cell sampling. We are putting together a cell sampling for the molten anvil experiment. So the sample is placed inside this octahedral, and then we have like a linear furnace for heating and a thermocouple for measuring the temperature. So after the cell sampling is assembled, so it will form a larger cube, and then this cell sampling will be placed in our 2,000-ton press. And this is a walker type of module. So we compress the cell sampling from the 111 direction of the cube. So after we place the spacer, and then we pump oil to the lower chamber so we can compress our sample. And this is my student, former student who is doing the experiment, so we can control our the heating using the computer. And we often fly to Chicago from Hawaii to do experiment using the advanced photon source at the Argonne National Laboratory. And this is a typical setup, Paris Enneberger press setup at the sector 16 BMB. And then we use the setup to measure the viscosity of iron nickel carbon liquid. And then this is like a probe sphere method. So I will give you so this is an overview slide about the techniques that we use for our research. Typically, there are two types of static high pressure techniques, diamond anvil cell and a large volume press. So there are varieties of diamond anvil cell that we use. One recent one that we use very much is the BX90 cell. So we place a heater in the diamond anvil cell so we can heat up the samples at a high pressure. And this is a technique that I'm going to cover at the later part of my talk. And then those static high pressure techniques can be combined with diagnostic probes. So we often combine it with synchrotron X-rays, neutron source, and then laser spectroscopy. So if the sample is recovered from the high pressure experiment, and then we could use electron probe to analyze the composition of the sample. And then the so typically the sometimes we also combine the electrical resistivity and ultrasonic setup for the measurement in multi-angle press, and then the electrical resistivity setup can also be used for diamond angle cell experiment. And this is the 3 presses in our multi-angle press laboratory. We call it the MAP lab at the University of Hawaii. On the left, this is a 2,000-ton press, and on the right here, it is a 1,000-ton press. Both presses have the Walker type of module, and then we also have the ultrasonic and the electrical resistivity setup for the multi-angle press experiment. And then we have another press. It is a cubic press. It's a 250-ton press. So this press is being setting up for experiment 2. For the diamond angle cell, if we want to so generate a high temperature, so there are typically 3 ways that we can heat up samples in diamond angle cell. One way is the external heating and the internal resistive heating. So those for the external heating, we placed a micro heater around the diamond, but for the internal heating, we actually placed the heater inside the sample chamber. And the laser heating that so people have been using a lot in either in the lab or in or combined with synchrotron techniques. So we shine high power laser to the sample in the compressed in the diamond angle cell. For experiment that require like a small variation in temperature and a stable heating, typically we think that the external heating may be a better approach in doing experiment for longer duration. So that's why we invest a lot of time and effort in developing the externally heated diamond angle cell for our experiment. So my talk basically have 3 parts. So first, I will talk about carbon in planetary cores, and then it's followed by the deep carbon cycle during the slab-mantle interaction and the genesis of super deep diamond. And the last, I will talk about the melting and elasticity of high pressure ices using the external heated diamond angle cell technique that we have developed. And then I will, at the last, I will talk about how I can use the FOSS facilities for my future project. As we all know that the Earth's core is mainly made of iron and nickel, but it should also have some light elements such as sulfur, silicon, oxygen, carbon, or hydrogen, because the density of iron at core pressure cannot match the seismic observed seismic determined values. So there is a so-called density deficit between the density of iron and the seismic values. And there's also a mismatch about the compression wave velocity and the shear wave velocity between the between that of the pure iron and the seismic observed values about the Earth's core, the Earth's outer core and the liquid core. So in this talk, I will mainly focus on carbon as a light element in Earth's core. Carbon, when alloyed with iron at high pressure, it will form those 2 types of iron carbide. Fe3C and Fe73. So both has different, so those phases have different structure, and with Fe73 has a higher carbon content. So the physical properties of those iron carbide phase would be very important for us to understand carbon in the Earth's inner core. So we utilize the techniques is so-called nuclear resident inelastic X-ray scattering, NRIX, available at sector 3 of advanced photon source. In this experiment beamline, so there's also X-ray diffraction and extinction most power techniques available. So we loaded our sample synthesized in molten envelope. So the sample is iron 57 enriched Fe73 and the Fe3C in a diamond anvil cell. It's a diamond anvil cell called the panoramic diamond anvil cell with a 150 micron cubic diamond. So we compress the samples at the room temperature up to 1.5 megabar. And then we collected the NRIX data for the sample. So the NRIX data could give us the device on the velocity. And then if we, so we have previously determined the equation state of Fe73 phase. Now, so using these 3 equations with 3 variables, then we can calculate both the compressional wave velocity and the shear wave velocity. So from our experimental data, so we can see that is a pronounced drop in both absolute value and also the rate at which the bulk sound velocity would increase with density. And then there's a similar drop also in Vs in the shear wave velocity and the shear modulus. And then this is corresponding to the panoramic, paramagnetic to non-magnetic transition, which has been confirmed by our X-ray emission experiment. So this is the high spin to low spin transition for iron. So we extrapolate our data to the Earth's inner core condition based on the Virtue's law. So we can see that by alloying iron with a carbon to form iron carbide phase, so it can reduce the compressional wave velocity and the shear wave velocity of iron, and like bringing it closer to the seismic observed values. Another very important parameter for the Earth's inner core is the Poisson's ratio, so which is defined as a function of Vp over Vs. So the Earth's inner core has a Poisson's ratio close to 0.45, but most of other, like including iron and iron nickel alloys and other iron light alloys, they have a Poisson's ratio that is much lower, which is below 0.35. And our iron carbide phase, it has, so after the spin transition, it has a Poisson's ratio that is closer to the seismic observed values. And this is also this also agree well with one of the theoretical work about the Poisson's ratio over iron and iron carbon alloys at high pressure. So by increasing the amount of carbon in iron alloys, you could elevate the Poisson's ratio. So we observed by extrapolating our data to the inner core pressure. So our Vs and of both iron carbide phase are closer to the prime values. If you look at the Vs of pure iron, so it exceeded the prime value by more than 65%. But our values are closer. If we consider the temperature effect and range of the inner core pressure, so we could estimate the volume percentage of iron carbide phase in the Earth's inner core. So if Fe73 is stable in the Earth's inner core, then let me close the door. So if we have an inner core boundary temperature of 6,000 Kelvin, so that will be like 30 volume percentage of iron carbide phase together with iron, so that we can match the VS of the Earth's inner core. So now we change gear to the Earth's liquid outer core. So we will measure the viscoelastic properties of iron nickel carbon liquid by both experiment, and we also computed those properties by first principle molecular dynamics calculations. So as we know that like a lot of this terrestrial planet has a large liquid outer core, so the elastic and the viscoelastic properties of the iron-rich liquid will be very important for us to understand those planetary outer cores. And this is so we used, as I said, we used a combined approach from both experiment and the computation to determine the viscosity, density, and the sound velocity of those iron nickel carbon liquid at high pressure. So for that, we use the experimental setup also at a sector 16 BMB. In this beamline, there's a Paris-Enderberg press that is used to compress our samples to high pressure and heat it up to high temperature. And this project was led by my former graduate student, Dr. Xiaojing Lai, who is now an associate professor at the China University of Geoscience. So the experiment, in this experimental hutch, there is a solid state detector and a high-speed camera, so that we can get X-radiograph images of the samples at simultaneous high PT conditions. The X-ray diffraction, the energy dispersed X-ray diffraction pattern of liquid phase is very distinctive from the X-ray diffraction pattern of solid phase. So this is the black line pattern is the X-ray diffraction pattern of iron and nickel mixed with carbon, and after it is molten, so we can just see a bump like in the X-ray diffraction pattern. So we measured the X-ray diffraction pattern at various theta angle for iron nickel carbon with 5% carbon and iron nickel with 3% carbon. So after we measured the multi-angle energy dispersal as a diffraction pattern, so we can determine the total structure factor of the liquid as a function of pressure up to 7 GPa. And by doing a Fourier transformation of the structure factor, so we could get the pair distribution function of this liquid at high pressures. So basically, the pair distribution function is that if you have a center atom, so this is a possibility of finding another atom around this center atom. And this is the blue line here shows is the first coordination shell, and the red one shows is the second coordinated shell. And then in the second, as we can see from the PDF, so the second shell has a main peak and the satellite peak. So we perform the spectral analysis of the peak position of the second shell peak. So we found that there's at about 5 gigapascal, 5 GPa, so there's a substantial reduction in the in the the second shell R value, the position. So this is indicative of pressure induced liquid structure transition in this liquid. So to understand this, the liquid structure of iron nickel carbon liquid at high pressure, so we also performed the first principle molecular dynamic calculation in collaboration with Dr. Jianwei Wang from Louisiana State University. So we simulate this large cell. We simulated this large cell, and then in this large cell, so we can identify those 4 different types of connection motifs. And then from the calculation, so we see that this if it is above 8.4 GPa, basically above 5 GPa, so we find that there is an increase in the fraction of this fixture or 3-atom connection motifs. So the increased fraction of these motifs, as we know that this configuration is a steepest configuration, so we should expect that there may be an increase in the viscosity if the liquid is above 5 GPa. So we further performed our experiment in this same beamline, but we used the high-speed camera and the viscometry to do this viscometry measurement. So we placed a sapphire Al2O3, the aluminum oxide sphere, in iron nickel carbon mixture. And then after the sample is molten, so this sphere would float to the top of the sample chamber because the density of this sphere is lighter than the iron nickel carbon liquid at high PT conditions. And this project was led by my former postdoc, now a professor at the China University of Geoscience, Dr. Feng Zhu. And this video shows, which is 10 times slower, which shows the floating of the probe sphere in the iron nickel carbon liquid after the sample is molten. And then we can see that from by analyzing all the images that are collected by the high-speed cameras, so we find that there's for tens of milliseconds, this probe sphere reach terminal velocity. And from the terminal velocity, we can use the Stokes equations with those correction factors, so we can calculate the viscosity of the liquid at high PT conditions. So this is our experimental result. So we measured the viscosity of iron nickel carbon with 3% carbon and iron nickel with 5% carbon at around 2000 Kelvin. So we find that there is an increase, substantial factor of 2 to 3 increase of viscosity across this 4 to 5 GPa. So in previous work that we found that there is a structure transition in the liquid. And this jump in the viscosity would have some implications about the dynamics of the planetary cores. So if it is a smaller core like the Europa, so this viscosity change might be occurring in the liquid core of Europa. But for moon or some larger satellite or moons, so we can see that we have to use this for any for any type of simulation. We need to use the higher pressure, the viscosity of this high pressure liquid phase, so which is more viscous for the iron carbon liquid. So we also performed first principle molecular dynamic simulation to calculate the viscosity of this iron nickel carbon liquid at a common boundary pressure and inner core boundary pressure and temperature. And we found that at the inner core boundary pressure, so we can see that the viscosity like increase from the CMB to ICB. And then we also find that with increasing carbon content, so we can see that the viscosity would be lower. So would be like a low. So would be lower. So it would be more viscous. Like comparing with some other iron alloys like iron sulfur or iron liquid. So iron carbon liquid are 3 to 4 times more viscous at a pressure higher than 5 GPa than iron sulfur or iron liquid. So this would also have some implications about the percolation velocity of the iron carbon liquid in silicon mantle. So during the core mantle segregation, so during the formation of the core. So the iron carbon liquid may be much slower than the percolation of the iron carbon liquid may be much slower than that of the iron and iron sulfur liquid. So during the formation of the core. So in summary, so we found there is a structure transition in iron nickel carbon liquid at around 5 GPa. So this has a substantial effect on the viscosity of those liquid at high pressure. So the viscosity would increase after the phase transition. So for the Earth's for Earth's planetary liquid outer cores, so density is one of the important parameters that we also use to compare with seismic observed values. So the density of the Earth's liquid outer core, as we know, that is 10% lighter than pure iron, and the compression wave velocity is 5% faster than pure iron. For the moon, we have very limited knowledge. So based on some work, is the compression wave velocity of the liquid outer core of moon may be slower than pure iron. So we utilized also the same experimental setup, but we used the another technique is called the X-ray absorption techniques to measure the density of iron nickel carbon liquid at high PT conditions. So this is again led by my former postdoc, Dr. Feng Zhu. So in the experimental setup, so this self-sampling shows that we have our sample in alumina capsule. And then we also have this alumina as a reference for the density. And the MgO plus platinum is a pressure marker. So the X-ray absorption experiment is set up like this. So we can focus on the reference material, which is alumina. So using the X-ray absorption technique, and then we can see the absorption profile of the alumina phase. So which can be calibrated to the density of alumina at those PT conditions. And then we also collected, focused on the sample. So we collected the X-ray absorption coefficient, profile across the sample. And then we can calculate the density of the iron nickel carbon liquid at high PT conditions. And this is the representative refinement of our X-ray absorption data at a 5.5 GPa and 1873 Kelvin. And from this data, we can see that due to melting, there is a decrease in the density of the melt. So we performed the experiment for those two compositions, iron nickel carbon liquid, and then we fitted the equation state to the to our data. So so from our work, so we can see that by increasing the amount of carbon, we see a lower density for the iron nickel carbon liquid. But our experimental result is only up to like 8.5 gigapascal, so which is still far away from the Earth's liquid outer core. So we also performed the first principle molecular dynamics calculation to extrapolate the density determination of those iron nickel carbon liquid to higher pressure. So in this run, so we extrapolate to 60 GPa, and then we also extrapolated to much higher, so even higher than the liquid outer core condition. So from that, we can have a better way in constraining the density of the iron nickel carbon liquid under the Earth's core condition. And our liquid density from our experiment, it compares pretty well with the calculated result for the density of iron nickel carbon liquid. So this is our result for the equation. So if we use the compressibility and then also the density of this iron nickel carbon liquid, then we can calculate the compression wave velocity. So which, as we can see, that is higher than the prime and the compression wave velocity of pure iron. And in terms of the density, is actually much lower than the prime values. And it also has a shallower slope than the prime values. So this mismatch of the slope and the absolute value implies that a carbon cannot be the sole light element in the Earth's outer core. So there should be some other light element that can really make the velocity and the density profile much better. So we have discussed about the deeper carbon cycle. So during the early Earth, or like in the Earth's like a metallic core, but in the later section, so we are going to talk more about the deeper carbon cycle in so during the slab mantle interaction. So this is a work that is led by my graduate student, Dr. Xiaojing Lai. So there's a recent work about like diamond inclusions, the iron nickel carbon sulfur inclusions in the super deep diamond. So that's an indication that so during the formation of those diamonds, so there may be metallic iron may be involved during the formation of the super deep diamond. So the redox reactions between the subducted carbon or hydrogen and the iron in the mantle may be responsible for the formation of the diamond, like in the transition zone or deeper. So in this work, we determined the melting of the iron carbon hydrogen system by laser heated diamond animal cell. And then this is the experimental setup that we use. We loaded our sample in the symmetric diamond animal cell, and our sample is iron with the carbon hydrogen source around it. And then we also, our sample was also iron carbon alloys with like a reaction with those iron hydrogen source. So the experiment was performed at sector 13 IDD of the APS. And this is a summary of our result. So we found that by reacting iron with this carbon hydrogen source, so we found the formation of the diamond in this one. So when we heat it up to 1885 Kelvin, so we found the diamond, the formation of this powder diamond from the reaction. So we performed a series of experiments. So we found that there is this type of phase diagram. So we at a higher pressure, so the iron hydride may be more stable than iron carbide. And when the iron hydride is more stable, so basically hydrogen would kick carbon out from the iron carbide phase to form diamond. And so those will be like this reaction. So that means the iron will prefer hydrogen to carbon at a higher temperature in our experiment, like as determined from our experiment. So we also determined the melting of the iron carbon hydrogen system in laser heated diamond cell. So when we heat up the sample, so we can see the diffuse scattering signal from the sample. So this is an indication of melting in our experiment. So we look at the increase of this diffuse scattering background here, and then we determine that where the initial melt would form. So in these two cases, like at the 23 GPa, so the initial melt was formed at 2139 Kelvin, and then at this pressure for the iron carbon system, and at this pressure iron carbon hydrogen system. So although it is at a similar pressure, but the melting temperature, the initial melt formed at a lower temperature. So we summarized all of our experimental result, so which shows the melting the melting temperature of our iron carbon system. So this is the melting temperature of the iron carbon system and iron carbon hydrogen system. So we can see that by increasing, by alloying carbon with iron, so you will lower its melting temperature, but by adding hydrogen to the system, so you can lower the melting temperature even further. So if we compare our melting relation of the iron carbon and the iron carbon hydrogen system, so we can see that especially for the iron carbon hydrogen system, so the melting temperature of this system is lower than the mantle geothermal temperature. So this would indicate that if you have carbon and hydrogen source was carried by the subducting slabs, and then which reacted with carbon with iron in the mantle to form the iron carbon hydrogen alloy, and then in the mantle just when it's closer to the mantle geothermal condition, so this iron carbon hydrogen would be molten, and then this would create an ideal environment for the formation of macro diamond under those high pH conditions. And then if you have a hydrogen in the system, so that would further facilitate the formation of the diamond from the iron carbon hydrogen liquid. So I think I'm running out of time a little bit, so I will just jump to the next topic, so which is melting and elasticity of high pressure ices. So as we know that high pressure ices are present in many planetary environment, such as in the interior of those moons of Jupiter. And the ice could also be present in some cold subductive slabs. So if you compare the phase relation of ice with the mantle geothermal, the geothermal of the slab. And the ice is actually now has at a high pressure. Ice 7 is actually a mineral name because it was found as an inclusion in the superduper diamond. And then those superduper diamond could origin from the top of the transition zone or below the transition zone. And the ice phase diagram is actually pretty complicated. The most recent work by Volatile shows that there may exist a superionic phase. So then if there's a superionic phase, then that would indicate there may be a kink in the melting relationship with pressure. So that means the ice would melt at a higher temperature than so then if we extrapolate from the lower pressure data. So we have spent a lot of effort in trying to do those external heated diamond cell, which is not always straightforward. So we start from machining the ceramic heater base and then winding the heater to the base, and then we how we put it together, it's actually make quite a difference. So we published a paper is in the journal Visualized Experiment. So it has a 7-minute video showing you how to prepare external heated diamond cell. So you may want to check it out. And we also move it a little bit further. So we designed this LH-DAC enclosure, which is supported by compress and later Jesse cars. So this enclosure has both, it's water cooled, has a bidirectional pressure control. So which is very important because if you increase the temperature, the pressure would vary. So during the temperature, so during heating, and it has a vacuum or inner gas atmosphere. So so the enclosure, by placing the external heated diamond cell in the enclosure, you can protect the diamond. And it has a large opening angle. So this setup has been used in various beam lines, including 13 BMD, so which has a Brion scattering setup. And then in like last year, we made a few attempts in heating the sample to more than 1400 Kelvin by applying around the 2050 watt. And this is a picture shows the light that come out from the heater in the external heated diamond cell, which also indicate that the heater has very high temperature. And after we took out the external heated diamond cell, so the diamond is intact, and also as you can see, the tungsten wires that we use to reach this high temperature appears to be also intact after heating to 1400 Kelvin. And we also tested in the Raman lab at the Jesse cars. So we performed some experiment by collecting the Raman spectrum of some carbonate at high pressure. And then we observed decomposition of those carbonates at high PT conditions. And this experiment was performed up to 1000 Kelvin. So we utilize these newly developed techniques to determine the melting by XRD, and for the samples loaded in the external heated diamond cell by fine-tuning the PT conditions. So this is just an example that shows that at this temperature, 6.4 GPa and 550 Kelvin, so we can see the diffraction peaks from ice. And then, but by just increase 25 Kelvin, and then you can see the ice become more single crystal. And then after a while, so you can see if the ice become more or less single crystal. And then we stay there for a little bit of time, and then even at the same temperature, so we see the disappearance of the single crystal peaks for ice. So that means the melting temperature is very close to 575 Kelvin at a 6.1 GPa. Because our enclosure has this bidirectional pressure control. So if we only applied some pressure, like 0.2 GPa, and then we can synthesize single crystal. So then we can like really pinpoint the melting temperature of I7 at 575 Kelvin would be between so at this temperature, so the melting temperature is 575 Kelvin. So we have performed many experiments to determine the melting temperature by fine-tuning the pressure, and then by melt and synthesize single crystal. And then we can see that there is our lower temperature, our lower pressure data agree well with previous work, but at pressures higher than 12 GPa, so that appeared to be a kink, and which indicative there may be a phase transition at a higher temperature for this pressure. So by using the external heated diamond cell, so we could synthesize a very nice single crystal of I7. So those are the single crystal data of I7 at high PT conditions. And this sample is molten, as we can see. So from that, from the data, we determined the thermal equation state of high pressure ices to around 80 GPa. So this work has been published in American Mineralogist. And then we also performed some preliminary work on the Brion scattering of the single crystal of the synthesized single crystal I7. As we can see that we can get both actually VS and the VP for the single crystal data, and so for the single crystal ice. So in summary, so we have developed those resistive heaters and this LH-DAC enclosure for simultaneous high PT condition, high PT experiment above 1400 Kelvin. So potential applications for this technique would include the materials and also the structure and elasticity determination of materials at high PT conditions. Even like water rock interactions and phase transitions and the thermal equation state of minerals and materials under extreme conditions. So I was asked to talk about the force. So I really look forward to the commissioning of the force facilities, especially the very large volume press at force. So my wish list that we want to synthesize a large standard or performing like those high pressure geochemistry type experiment up to the mantle transition pressure or even the lower mantle conditions. So which often requires large sample volumes and with controlled like oxygen fugacity, and then maybe we can accommodate multiple samples in the same run, and then we could also place capsules, even double capsules, to seal fluid or melt under high PT conditions. And then, for synthesizing larger crystals, you might need long duration reactions. So I will just go through some pictures about our labs. So if you want to know a little bit, so we have those supporting facilities. So our multi-envelope lab for a single PI lab. So it's not at the same scale as FORCE, but yeah, so that's what we have been doing. So we have this CO2 laser that we can cut the paper gasket for the multi-envelope cell assemblies. And then I wrote those softwares in LabVIEW to control the PT of the multi-envelope press. And then we also use 3D printer to print out this mode called the semi-injection mode to just make those pre-gasketed octahedron that can be used for our high pressure experiment. And this is the precast octahedron that is made from our this semi-injection mode. And then we calibrated our cell samples of those. And then this is our attempt for the high pressure geochemistry research on the carbon isotope measurement using ion probe. And then the facility like a source would be the 6,000 ton press in force would be very useful for this type of research. So with that, I would like to conclude my talk. I'm sorry that I run a little bit over time.
Thank you, Ben. That was a great talk. Your diamond anvil cell is super cool. I see some applause in the audience. And then do we have any questions for Dr. Chen? Let me check the chat too.
Can I ask you? Hi, I'm Kyusei Tsuno from Arizona State University. I have a question. So you investigated the effect of carbon on viscosity as well as sound velocity of iron nickel alloy, right? Then how extent is the effect of carbon on viscosity or sound velocity compared with the effect of sulfur or silicon or phosphorus or some other light elements? If you remember the other effect of other elements, and maybe could you please explain?
Oh yes, so we have in one of the figure, it's particularly for viscosity. So in one of the figure, I showed that before the structure transition, the viscosity of iron carbon and iron iron or iron sulfur alloys, so they are pretty similar. So they are at least at the same level. But we found that after the structure transition at the 5 gigapascal, so the viscosity of iron nickel carbon would increase, would be higher, like a factor of 2 to 3 higher than that of iron sulfur and liquid iron.
Oh, okay, thank you.
Hi, Binchen. This is Tintin. Can I ask you a question?
Oh, yes, sure. Please.
Yeah, very nice talk and very informative. So I'm interested in your study about the iron react with hydrocarbon and form diamonds. So I'm wondering, did you have a chance to using Raman spectroscopy to analyze the carbon hydrogen molecular after the reaction? And is there any possibility other methane or other hydrocarbon molecular can be formed after this reaction on the high pressure?
Yeah, we have attempt to do that. So we have one sample that is we try to see if there's any methane that can form, but we actually couldn't detect any signal. For diamond, we performed some experiment in the diamond anvil cell, with a sample in the diamond anvil cell. But the result is not conclusive because we know that we have to put the laser so it will so we cannot discriminate distinct the signal from the diamond anvil or our sample. But from our XRD data, so we could see that there is the form the diamond they are powder, so which is very different from the single crystal diamond anvil.
Thank you.
We haven't done done the FIB, the focused ion beam. So it will be helpful to cut across the a thin section in the sample to see what if we can find a diamond there.
We have a
from
question.
our XR data, it's pretty conclusive that we have the powdered diamond forming from the XR data. Francesca.
Yeah, we have a question from Francesca Miazzi. Thank you very much for the talk, Ben. Everything you showed is extremely interesting. About the work with carbon, hydrogen, and iron. Do you have a sense on which processes would allow to bring iron in depth without it being tight to form water or CH4?
Yeah, that's a very good question. So the compound that we use, like iron, so this is C14H12. So like if you have like a methane, maybe so if it react with if you like have like a metallic iron in the system, so those metallic iron, yeah, it might react with the, yeah, as we can see that the high PD condition, it should react with those phases, this iron. So it like those carbon hydrogen phases. So to form iron carbide, or like and then so that's a very good question. Actually, in this experiment, so we actually did various experimental setup. So if you can see that this iron carbon alloy, you react with this CH compound, and then after reaction, it will form iron carbide. So that, yeah, if you look at this iron foil with this CH compound, if we use a laser to laser heat locally in this area, and then it will form iron carbide, and then some of the hydrogen will diffuse to the iron and to form iron hydride. So for this unheated area, so we can see very clearly that this the lattice of this iron would expand, yeah, because of the incorporation of hydrogen in the system. So iron carbon salts would readily react with iron. So if there's any like a metallic iron in the mantle.
So she has a follow-up question. Do you think it would be possible to have this reaction also if the iron is tightened with other compounds like carbonates or oxides?
Yeah, we haven't attempted yet. Like iron oxide, we haven't done that yet. We have performed some experiment for iron carbide to react with water to form iron oxide. Potentially have some like a carbon hydrogen like compound forming also too. But the iron oxide, I don't know actually. Yeah, without like doing the experiment.
Okay, she says, thank you very much. Okay, and that takes us over 1 p.m. Thank you, Dr. Chen, so much for coming and giving us this talk. Thank you for everyone for sharing this hour with us. And we will see you again in the fall.
Thank you very much.
Have a good weekend, everyone.
Okay. Bye.
Great talk. Thanks.
You mean in May, right?
Oh, so sorry. I'm sorry. In May for next.
Yeah.
Our last talk before the fall.
One more talk. Yeah.
Yeah.